everybody. I'm Melinda Todt. I'm an associate professor at the Eötvös Loránd University and a researcher at Altasoft. And today I would like to give you a talk about our journey, that how we applied our Erlang security checkers on Elixir code. Our journey began in 2023 in October in Berlin, when we had a talk at CodeBeam Europe, where we presented our static analysis-based security toolchain for Erlang. And obviously, during the talk and after the talk, lots of people asked that whether you can do the same for Elixir. And we said that, why not? It's on the roadmap and we will try to do. And today I'm here to present you that whether we succeeded or not. So let me just do a quick recap that what we've done. We have a static analyzer tool called Refactorer. It's a static source code analysis and transformation tool for Erlang. And what we've done is that we've used this framework and implemented and designed security checkers based on the analysis available in the framework. It's a static source code analyzer framework, so it gives us lots of nice features of static analysis. So we have call information, obviously, or different semantic information about the program entities like variable bindings or record usages. But the tool also features data flow analysis, and it has data flow information. So we can use that, for example, to calculate the origin of a certain expression or a certain value. We can have a call graph based on Refactorer's infrastructure, so we can perform different analysis where the call graph of the source code is needed, or we can perform control flow based analysis as well. Why those analysis is important in case of security analysis is the issue of false positive reduction. If you've participated in the talk just a few minutes ago, that was one question raised there, that how we deal with false positives. Because once you have a vulnerability detector, the main issue is to process the results, because in some cases, you might get a very long list of vulnerabilities, and the severity of the issues are not equivalent. Some of them might be not harmful at all. Some of them can be quite severe. So you have to do a kind of prioritization, that's what you wanted to deal with. And if a tool can help you to filter out and drop some of those false positives, that could be really useful. And we put a big effort on false positive reduction, and the framework that we have allows us to do it. So we can do, for example, taint analysis based on the data flow that we have inside the Refactorer framework and filter out lots of false positives. It's quite efficient. We can drop out more than 30% of the hits using our framework and our algorithm. So what we have so far is that we analyzed plenty of open source Erlang projects, and we found more than 500 vulnerabilities in those projects. So we have to say that security analysis is something that is really needed for Erlang applications. The majority of the issues that we found relates to denial of service attacks through atom exhaustion. The majority is around 70%, so it's really a big issue that we have to handle, or you have to handle if you have an Erlang application. But we found injection-like attacks when you are using an OS command with unverified input or some unverified code loading, dynamic code loading to the beam. We also found race condition related issues through, for example, ETS, unsafe ETS table traversers or process linkage. And a few man-in-the-middle typed attacks also discovered in Erlang code related to unsafe cryptographic or outdated cryptographic library usages or unsafe network configuration. We have an additional category that's called the deprecated or removed cause. You might say that it's not really a security issue, but it may cause to denial of service attacks. So we consider it as potential issues that you have to consider in your application. Let me just point you to real life use case examples. We used our tool chain and analyzed the source of RabbitMQ. We found vulnerabilities in it. A particular vulnerability was analyzed by refactorer, and we've created and calculated an exploitation path to that vulnerability through the data flow reaching of the tool, and through a found API call, we were able to crash a RabbitMQ node. Another example is the OpenID project. With Safe, the tool that we built on the top of refactorer, we've analyzed the OpenID project and found denial of service related issues in the project. We've reported it to the developer. It was already fixed I think 2 weeks ago or a week ago. So we've reported the issue, a CVE is created from it. And now if you wanted to use the OpenID, we can say that it is safe to use. So that was the history. And now we are at the point that whether we can do it for Elixir. And you can say that, okay, you are talking about Erlang analysis, but Elixir is not Erlang. So Elixir can be secure. The issues that you listed relates to Erlang, but now I can say that neither Elixir is secure. We've analyzed a few Elixir projects, not as many as in case of Erlang, but we found more than 300 vulnerabilities in those applications. So we have to say that neither Elixir systems secure. So Elixir systems have some security issues that the developers has to deal with. Obviously, if we already identify that Erlang has some issues to deal with, then both of the languages run on the same beam, on the same virtual machine, so they have something in common. Elixir inherits lots of issues using Erlang libraries, sometimes not in an obvious way, sometimes it's hidden by certain Elixir constructs, but at the background, there are some Erlang-ish library calls that makes a certain Elixir expression vulnerable. And some new vulnerabilities also introduced by the language. Luckily, the Erlang Ecosystem Foundation has a security working group, and the security working group working heavily on giving guidelines for Erlang and Elixir developers or Beam developers for the Beam ecosystem to build guidelines how to build secure applications on the top of the Beam. So you can just read the guidelines, the secure coding recommendations, and follow those, and hopefully you won't have security issues in your code. Recently, they also focusing on web application security. So if you are designing a web application, then you should follow the best practices they are listing on the web page. But if you are just starting a project, you can read those guidelines carefully and then say that, okay, I will follow all of them and keep in mind in all of the rules and will not have any kind of issues. But obviously it's not, it cannot be applied to all of the developers. And we have existing tools, existing software, and to detect all of the vulnerabilities that we have in these projects cannot be done manually. So we need tools that support the identification of the vulnerabilities. And for Erlang, we have the static analyzer framework refactorer, and we built a security auditing tool called SAFE on the top of the analyzer framework of refactorer. So we are at the point where you can ask, and it was asked actually in October in Berlin, that whether SAFE can identify vulnerabilities in Elixir code as well. So let me just transform the question, because it's not SAFE, but that should handle Elixir code, but the environment it's using. So whether refactorer can identify vulnerabilities in Elixir code. And once we know that refactorer is a static analyzer tool, we might rephrase the question again and ask that whether a static analyzer tool that was designed originally for Erlang can handle Elixir code and identify efficiently vulnerabilities in Elixir code. Obviously, you can add as many plugins and extensions to a tool to handle it, but obviously our main goal was to reuse the existing infrastructure as much as possible. And now we are on the stage that when we can say that, yes, it's possible to use a static analyzer to identify vulnerabilities in Elixir code. And let me explain you the process that how we do it. So when you wanted to identify some patterns, some vulnerable code snippets, basically you have this source code as an input. So you have this source code, but if you wanted to apply static analysis methods, you have to build an intermediate source code representation from that. In case of refactorer, that source code representation is a graph representation. It's a graph that's called semantic program graph, which is a 3-layered graph. It contains the lexical information, so all the token information about the original code and the preprocessed code as well, all the tokens, just to be able to preserve the original code as well. It has a syntax tree. Obviously, that's the base of our analysis, and it extends it with semantic information about the program entities. When I'm talking about data flow is part of this semantic program graph, and it is a kind of semantic information that the tool has. Then when you have this representation, you search for certain patterns on that representation. So that is the vulnerability analysis. You are looking for certain constructs, mainly using the syntactic and the semantic information that you have in the graph. And then the next step is to filter the initial candidates, filter based on semantic information, such as data flow, control flow, etc. So you filter out the results and drop all the candidates from the list where you are sure that these constructs are not vulnerable. And once you have the list of candidates or list of vulnerabilities, you wanted to present it to the user. And that's another issue, that how you do it, because obviously you have the findings on the graph level. So you have graph nodes that presents a certain that represents a certain language construct, but you do not want to, sorry, I just lost my focus in my presentation, but hopefully you have the good view. Can you still see my screen?
I see it, and then you zoomed out a bit.
Okay, just, is it full screen now?
Yeah.
Okay, thank you so much.
Mm-hmm.
Sorry. So the question is that we do not want to show the graph node itself, but we want to somehow map it back to the source code and to show the results, the vulnerability in the actual source code to the user. So once we wanted to turn it to an Elixir analysis, the first thing is that what you may, or the first idea is that, okay, we know that we can print the Elixir code to Erlang. So you have an Erlang analysis. Let's just analyze the Erlang code, the Erlang-ish version of the Elixir code, and then we will have the vulnerabilities. But obviously it's not enough, because the very last step, what I just mentioned to you now, that we wanted to map back to the results to the original code, that is completely impossible to do. So that is not working. But instead, the very first step, that how we create the intermediate source code representation, is based on the beam files. And since Erlang and Elixir, both of the languages compiled to the same beam, and if you compile the code with debug info, then you will have the abstract code built into the beam file. We can take this abstract code as the base of our analysis. And what we have to do is to create the semantic program graph from that. So not from the text, but from the abstract code. We map the abstract code to the syntax tree, so the syntactic part of the semantic program graph, run the analysis, all the analysis, the semantic analysis that we have, and that will result the semantic program graph, and then we can perform our analysis on that graph. Luckily, Erlang and Elixir shares the same semantics on the abstract code level. So once we have an abstract code, it could be either generated from Elixir or Erlang, the semantics of the same. So when we are performing semantic analysis on the top of it, then the result is equivalent. So we take this graph, and once we have this graph, we can perform the syntactic and semantic based searching for candidates in that graph. So what we've done is that we've applied the existing checkers that we had for Erlang, because that has a value for Elixir. One reason is that sometimes you call Erlang library functions, so you might call vulnerable library functions as well. But on the other hand, there are some constructs that is translated to Erlang calls, which is vulnerable. Just think about atom creation, so atom generation. And then we use this representation and the information stored in it to do the false positive reduction and the filtering the result. So what we do then is that we have to filter out that what are the false positives. We can do it on different level. Originally, I said that we do it on semantic level. And the question is that why it's important. It's important because if you just consider lexical or syntactic information, it has no knowledge about the semantic context of a certain expression, of a certain vulnerability. So once I have the 2-atom code snippet, just this, I don't know, 7 characters, depending on the context that where is it located, if I'm just looking on it on the lexical level, it can be, I don't know, some part of a comment or a part of a variable name or anything. So on lexical level, I do not have knowledge about that. On syntactic level, I have, because I know that, okay, it's part of an application, so it's part of a function call, so that may lead to a vulnerability because it's the 2-atom function call. But if we consider this simplest code snippet, we cannot decide just based on the syntax that it is a function call, that it's vulnerable or not. Let's just take this function, which is a private function, and we have an argument for that private function, and we just convert that argument to an atom. It's just a simple conversion, but nobody can access it. So if we track that, what is the origin of that value of the argument of the 2-atom call, we cannot find any public API. We cannot trace it back to any public API that, okay, it might be vulnerable because somebody can access it. It's a private function. So we further have to analyze the context of this call. So what we do is that we are looking for the traces, for the flow of the data, the origin of the data, that where the values might flow to that certain function call. If I have a function that calls it with a constant value, then I shouldn't report it as vulnerable because it's just a single atom creation. So nobody can do an iteration and generate different values to overload the atom table. So if we have this code snippet, we can say that, okay, it's not vulnerable. It's a false positive hit. So we can delete it from the result. But if we have an application where we have an input value for the bad guy function that is originated from an API, an external API of the module, and that is, in this case, especially a container. And if I just make this container even bigger and bigger and providing lots of input to the guy's function, then I can generate more than 1 million atoms, and then it results the beam to crash. So we have to analyze the context. And if we have something like that, based on data flow, we can say that it's vulnerable, and this is not a false positive hit. Let me just give you another example where we have a construct which doesn't seem to be an atom generation, because we don't see the 2-atom call or any kind of sign that it's a vulnerable function call, but we know exactly. And based on the semantic analysis, we will know that this will be an atom generation. A binary 2-atom call will be generated from it. And since the argument of the binary 2-atom is coming from, again, with data flow analysis, we can decide that it's coming from the external interface of the module. We can say that it's vulnerable and report it as vulnerable. So the last question is that how we present. So once we have the filtered list, how we present the result. That's quite tricky, because I've told you a lot about the syntactic and the semantic layer. That's quite nice and easy to handle. But the lexical layer is not, to handle it is not straightforward. Because during the abstract code generation, during the compilation, we simply lost lots of information. So the lexical layer stored in the semantic program graph is a kind of approximation of the original layer. So we try to approximate the position based on the line information that is available in the abstract code. And during the presentation of the results, we try to show that, so the line information matches. In the Erlang code, we can say exactly the line and the position and the column information, so exact position information. But in the Elixir code, the only thing that we can have is the line information. So say that, okay, we know exactly that here is the binary to atom call, but here we can just show that, okay, it's at line 12. It's more than nothing. So our main findings are that, yes, we can do it. The framework is applicable. We have lots of reusable components, but definitely we have to add application-specific knowledge. So we had to define new checkers for Elixir, and we are continuously developing our framework to add more and more checkers. We implemented and provide all of the checkers that covers the secure coding recommendation of the security working group. And what we are doing now is that we are experimenting with the web application related issues as well. We've already have checkers for cross-site scripting and remote code execution, but there is quite a long list in the EF web page, so we have to work on it further. So I would like to stop now and thank you for your attention. And I'm happy to answer questions now. And let me just introduce you to my colleagues who are present there at the conference. So you can ask Daniel and Robert and Dolly. I don't know whether they are there, but you can ask them about SAFE and about the analysis and what we have. Thank you for your attention.
Thanks very much, Melinda. So again, if anybody has any questions, please share on the Whova app. I'll give you a moment. If you don't have anything, I have a quick question. Okay, well, maybe while we're waiting too. So I'm curious, you were talking about sort of identifying when things are problems, like if it's a static variable, that's fine, but if it's maybe coming from a variable, then that's a problem. I'm curious, just from being a web developer, whether you've thought about having some way to identify, maybe even automatically, like these are going to be coming in from a controller or some API, and being sort of like highlighting those, especially being like, oh, this is user input, this is going to be coming externally, or is that all been manual analysis of the results?
Basically, whenever you have the controllers and that kind of stuff, so lots of things are generated and already present in the Beam code. So whenever you have the Elixir code, this is what I'm talking about, the hidden dependencies. So you do not see actually in the code, but since we are working with the Beam code, then lots of things is generated and we see exactly that there is a type of vulnerabilities, and we can do the data flow on the generated code that will include the dependencies and include the data flow inside the different between the different components. But we haven't done too much experiment with that. One thing that is an issue is that how we map back. So I think it's at some point it's easier to identify than to map back to the original code, because that will be in a completely different place than it is in the generated Beam file. But I think that, or I believe that we have to add lots of application-specific knowledge about the Phoenix application to make our data flow analysis more precise. Because as you said, so to connect the dependencies that is inside the Phoenix application or inside the application that you are using is not visible by the tool. You can add those actually, because if your dependencies or the framework that you are using is implemented in Elixir, like in case of Phoenix, then you can actually analyze it with refactorer. And if you added that source code and if we analyzed it, then we can track the dependencies and we can track the data flow through it. Obviously, it will take longer. So this is the drawback of static analysis. So as much code as you analyze, your analysis takes longer and longer, but it's possible because the code is implemented. So the framework that you are using is implemented in Phoenix, but in Elixir. But what I think is that if we add some shortcuts, so some kind of application-specific knowledge, then we can tune our data flow analysis to catch all of these dependencies.